Hey guys, how's everything going? This is JSer, who is not good at algorithms. I'm recording these videos to prepare my interview next month. In this video, I'm going to take a look at 5 to 8 random pick with a weight. Let's take a look. Given an array W of positive integers where each element describes the weight of index I, write a function pickIndex which randomly picks an index in proportion to its weight. Like for example, we're given input like this. It means the proportion to this index, which is 0, is 100%. So if pick index, we return 0. Okay, and then the 0 is the index. If we got an input like this, it means comparatively there will be 25% of chance that index is 0. And 75% of chance that it would be 1, right? If you just pick one and call it infinitely, it will almost return something like this, right? Cool. Let's try to see the real program interface. We're given a solution, which is a class, and we need to implement the pickIndex function. Remember that pickIndex will be called at most 10,000 times. Well, let's first think how could we pick, right? How could we mark the probability? Like in JavaScript, we have math random, but it's for math random, it will generate pick a number from 0 to 1, right? With 1 included and 0 included and 1 excluded. So if we got an input like this, like 1, 2, 3, how would we generate a random number in this range? Well, it's simple. We can say that, suppose that for number index, the weight is 1. We define a like a range, which with the length of 1, right? Like 0, 1. And for 2, of course, we start 1, and it will be 3, right? So and for 3, it will be 6. So actually, we could math random and multiply with 6. Let's add some weight. So it should be something like this, right? No, 2, 1, 2. Oh god, this is 1. This is 2. 1, 2, 3. Yeah, this is 2. And 1 through 4, 5. This is 3. Actually, we could use math random times the length, right? Total length, and use math floor to get the interval index. Like for this case, we get, like this case, we math random times 6, and we can get 0, 1, 2, 3, 4, 5, right? So the problem becomes, if we get an index like 0 to 5, how would we map it to the original 1, 2, 3, which is 0, 1, 2, right? Yeah, so actually that could be just, we can do some search, right? Like say we got 3. So of course this is the interval. We could search it from left to right, but it will cost us linear time. Well, which is not linear time. Actually, maximum would be oh yeah, it's the sum. So wow, it's very big. It's like this. So how could we do it? Actually, we could stop searching for this one, but only search it for the start index for each interval, right? Which means we will start from 1 n. Okay, the n interval. The first one is 0, 1, and 3. Right? If we got 4, we search it, and we get the last interval. Cool. So that's become a search problem, and it's ascending, so we can use binary search and improve the, if you use linear search, would be linear time. Binary search, it will be O log n, right? Yeah. That's it, right? So we need to get the index of this. This will be actually the sum, right? For at each index. Like for 1, the sum is 1. For 2, the sum is 3, and this would be 6. So that could be generated at the class initialization, and it will cost us linear time. And we have, so what we need? So what we need? A sum in array, and then binary search. Cool, let's do it. We initialize sums with empty. And for the first one, for the first number, it would be 0 to 1, and the second one is 1 to 3. So actually, we could, wait a minute. Yeah, let's first calculate the sum. Let's sum 0 for let weight of w sum plus weight. These sums, push sum, right? So we get the sum. We get the sum array. Like for input like this, we actually get a sum array of 1, 3, and 6. We now, if we get 0 to 5, we need to do the search, right? So the search result will fall to these 3, should fall into these 3 intervals. The 6 actually will not be, reached. Maximum it will be 5. So we search on 1, 3, actually with 0, right? The last one is actually how could we think about the search here? 1, 3, 6. We will actually search for the space between these numbers, right? For the first one, it might be smaller than 1, so actually the space between 0, possible 0, the space target is here, or here, or here, right? Cool. So actually we could start with the index, pick index here, and set a to index, and use binary search, pick the middle if small, and until the distance between these index are 1. And after that, we could just return the right one, right? Yeah, which means make the range smaller. Wow, that's clever. Yeah, let's do that. So to do that, we need to actually insert index at the beginning, which is 0, right? With 0, with 1, or with 6. So yeah, let's do the search. Before we do it, we need to generate a target. This one is simple. We just use math random times the biggest one, right, which is 6. And set a floor. Because the random is actually, the right boundary is not included, we floor it. Now, binary search, I equals 0, let j equals this sums length minus 1. So this is the range, right? I, j, we narrow it down. It will stop when the distance becomes 1. Every time we will remove at least one number. With one we only move one cursor, so there will be no overflow. Say ij is bigger than 1, like at the start, it would be 0 to 6, right? At first, it would be this 6. Let's go to this 0, 1, 3, 6. If we're going to search 2, let's see what happens. So if it is bigger than 1, the distance, it means there will be one middle number, right? Middle, of course, we choose the floor, plus j divided by 2. This is middle, which is like a 1. Okay. Now, if num is equal to this sums middle, if it is just equal to it, then actually we've got it, right? We will finally fall into a range with a distance of 1, and if it is equal to it, then that is actually determined. We can break by setting j equals middle plus 1, I equals j, I equals middle, and break. Okay, for the other case, if num smaller than it, like let's say there's a 7, we search 2 and find the middle is 3 because it's smaller than it, then it must be full to this half, right? And 3, it might be the boundary, so we will move j to middle. On the contrary, suppose case like this, we want to find 2, but it's bigger than 1, then 1 might be the left boundary, so this space might be the target. So we set I to middle, and then when the while loop is done, we fall into the final range, right? This the j will be the right, or I. We return I, right? We could return I. Okay, to make things clear, we return. Wait a minute. For j, for 2, and then we will fall into 1 to 6. And then we got 1, 3, right? So ij actually is the target, you see, is this. So actually, what we do, wait a second. This is the sum array. So J with the extra 0 put in, J must be subtracted with 1. Suppose this index like this. Actually, we get this is 0. We get this is the index would be actually result ij actually is 0 1 2, right? Index for index. So like for this, the real index would be actually subtracted with 1 because we push an extra 0. So the real index for the right boundary would be 1, right? Because we get 1 2. We get right boundary. Why don't we get left boundary? Because the 0 is an extra one. Actually, we're depending on the 1. If the 1 is 1, 0, then we return 0. 1, if it is 1, we return 0. If it is 3, we return 1, right? Like here. So what do? We return j minus 1. So this should work. Oh, the input is, there's no input. Let's try this one. Cool, let's submit. Yeah, we're accepted. Let's try to analyze the time complexity. Here, linear time. Here would be search for peak index. Actually, it's log n, right? Log n. For the space, we use an sum array. Well, and linear time. So from this problem, actually, we see there is a slightly difference between the binary search, exact search, or the just right or just left search. I mean, if you want to search for array, let's write it down here. If we search 1 2 3 blah 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 existence of n, we only check if it exists or not. So actually, we will use a while loop like I is smaller or equal to j, right? Even they are same, we can compare it to the target n. And yeah, and return false as default, right? But like say, like for 1 2 3, we find the insertion position of n, but there's a, yeah, something like this. How we do it? Well, for if the n exists, we can insert at any positions, right? So we don't care. If it is bigger than someone, than 2, we need to insert here, right? Actually, we are going to, so for this case, actually we're going to find a position where is I plus 1, find an interval which n will fall in at like this. If this one is the last smallest one, we could just start with I added. If this is not the smallest one, maybe we need to insert an empty empty node and make things happen. We can insert an infinity and search the range, search the interval, right? So this will actually make things easier. And we could just like we did here, we write a while loop while j is one element, at least 2 elements away from I. So it is stop. Actually, we can think of this a range, like a range. We can crush it, make it smaller and smaller. At last, it will fall into an interval with the distance of 1. Right? Yeah. So for this, we can do it easy like this. We don't need to care about. There's some trivial problems when we are choosing the middle index and do the comparison. I did something before. It's very error prone. For cases like this is left is not the biggest one. Oh no. Suppose that n could be inserted at here or here. Well, we just insert like infinity, blah 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 blah, like 1, 2, blah blah blah, infinity. To this. It will work perfectly, right? Shift and pop will cost us only constant time, so it doesn't matter. It doesn't affect the time complexity. Yeah. That's all for this problem. Hope it helps. See you next time. Bye-bye.